Okay, here we are with 3.2. We're going to look at some measures of spread. The objectives that we're going to take a look at here, we're going to compute the range of the data set. I'm going to compute the variance of a population and a sample, computing the standard deviation of a population and sample, approximating the standard deviation with group data. We'll use the empirical rule to summarize data that are unimodal and approximately symmetric. And then we'll look at Chebyshev's inequality to describe a data set. Compute the coefficient of variation. So a lot to do in this section. So let's get started. We're going to first look at the range. The range of a data set is simply the difference between the largest value and the smallest value. The average of monthly temperatures in degrees Fahrenheit for San Francisco are listed here. We want to find the range of these temperatures, 63 minus 51, and that will be 12. So, although the range is easy to compute, it is often used in practice. So the reason that the range involves only two values is the largest and the smallest, okay? Computing the variance of a population in a sample. When a data set has a small amount of spread, like San Francisco temperatures, most of the values will be close to the mean. When a data set has a larger amount of spread, more of the data values will be far from the mean. So the variance is a measure of how far the values in a data set are from the mean on the average. The variance is computed slightly differently for the populations and the samples. The population variance we're going to look at first. Okay, so here again we have our data, x sub 1, x sub 2, denote the values of the population in size n. Remember when we say population, we use that uppercase N, and mu to denote the population mean. So we have the population variance. Again, population variance, we have sigma squared is going to equal the sum of each piece of data subtracted from the mean and then squared divided by the total. So you take each piece of data, subtract it from the mean, then you square it. And I'll talk about why in a moment. And after you add all those together, then you're going to divide by n. So here we have the San Francisco temperatures. Let's take a look at that. We're going to compute the population mean, which is mu. So I'm going to take the sum of all of these numbers divided by my total in the population, which is 12. So I get my mu of 57.5. So for each population value, x sub I, we're going to compute, here we have the mean, here we have each number, then we're going to take every piece of data and subtract it from the mean. This is the difference right here. Each piece of data subtracted from the mean. Okay, that is this part. Each piece of data subtracted from the mean. Now, notice that we have some negative values and we have some positive values. When we're talking about distance, when we're looking at the spread, the distance, we want to use positive values. So one of the common ways in mathematics that we make things positive is that we square it. So that is why we're going to take each one of these and we square it. Notice now they're all positive. Okay? So we took the difference and then we squared it. Now we take the sum of those squared deviations to obtain 169. So we add all of these together to get 169. Then we're going to divide the sum that we got in this step by the population size n to obtain the population variance. So we have population variance, which is represented by little sigma squared, equals sigma times the quantity x sub I minus mu squared all over n. All of those symbols simply mean what we did here. We're going to take each piece of data, subtract it from the mean, then square it. Then add them all together. We get 169. And then divide by how many pieces of data we have in our entire population, which is 12. So our variance, our population variance here is 14.083. Now notice we have 0.83 once again up here. When we squared it, we had 2 places past the decimal, so we make this one 3 places past the decimal. Alright, so when the data values come from a sample rather than a population, the variance is called sample variance. But the procedure for computing the sample variance is just a little bit different from the one we use to do the population variance. In the formula, the mean mu is replaced by sample mean. That's not a problem, right? We know that when we talk about sample, we're going to use this. But the denominator here is n minus 1. And what happened is mathematicians went through and they noticed that there was a difference when they just divided by n and when they divided by n minus 1. And the n minus 1 made it much closer to what the actual variance was going to be. So thank goodness for the mathematicians that figured this out. And we just have to remember that when we are taking a sample and not the population, the sample variance, that we are instead dividing by n minus 1 and not just n. So when computing the sample variance, we use the sample mean to compute the deviations. For the population variance, we use the population mean for the deviation. It turns out that the deviations using the sample mean tend to be a bit smaller than the deviations using the population mean. If we were to divide by n when computing the sample variance, the value would tend to be a bit smaller than the population variance. So they show it mathematically, and I believe in your book they do show as well, that the appropriate correct is to divide by n minus 1 rather than n. So this is exactly why we just talked about dividing by n minus 1. Okay, you just have to remember that when it's a sample variance, you divide by n minus 1. Here we have a company that manufactures batteries, testing a new type of battery for laptop computers. They're measuring the lifetime and hours of 6 batteries, and there are the results. Let's find the sample variance. Okay, now see, they have a whole bunch of batteries testing a new type, so they're going to take a sample of just these 6. So this means we have a sample variance. So remember, the mean is now x bar. Add them all together, divide by the 6, I get 4. Now my sample variance, I take each one of those, subtract it from the mean. Each one subtracted from the mean. So 3 minus 4, 4 minus 4, 6 minus 4, 5 minus 4, 4 minus 4, and 2 minus 4. After I do that, I'm going to square each one. And then instead of dividing by 6, I'm going to divide by 6 minus 1, and my sample variance will be 2. Now we're going to take a look at computing the standard deviation of a population and of a sample. So the variance is computed by squaring the deviations. The units of the variance are squared units of the data. So in a battery lifetime example, the units of data would still be hours, and the units of variance would be square hours. In most situations, it's better to measure the spread having the same units as the data. So we simply do this by taking the square root of the variance. The quantity is called the standard deviation. So the standard deviation denoted by S and denoted by sigma would be the square root of your sample variance and the square root of your population variance. So your sample standard deviation and your population standard deviation. So the population variance of the temperatures in San Francisco was 14 and 83 thousandths. Find the population standard deviation. We simply would take the square root of that and get 3.753. The variance of the lifetime for the sample batteries is 2. The sample deviation would be the square root of that, which is 1.414, etc. We're rounding, obviously, okay? Now, some of you may have done standard deviations and variances in the past. One of the ways that I find that it's easy to organize it is putting them in an Excel spreadsheet. So if you're interested in seeing that, just let me know when we get together on Thursday, and then I can show that to you. All right, here we have our TI-84 plus. We're going to put our data in here. We're using our first variable statistics command again, and down here you will see your sample deviation and your population standard deviation. Right here are your values. So the same as before when we had this list in here, just hit your one variable statistics, and then that will give you your values. Now remember that a statistic is resistant if its value is not affected by much by extreme values. The standard deviation is not resistant. Why? Because we use the mean to find the standard deviation. And if the mean is not resistant, then the standard deviation is not going to be resistant. So the standard deviation is affected by extreme values. All right, now we're going to take a look at approximating the standard deviation with grouped data. So again, sometimes we don't have access of the raw data. We might have a frequency distribution. So once again, we're going to compute the midpoint of each class and approximate the mean of the frequency distribution. For each of the class, we're going to then take the mean, midpoint minus the mean, which we looked at in 3.1. After we do that now, we will square those values. And then we will multiply it by the frequency. Once we do that, we're going to take the product and we're going to add them all together. We're going to take the sum. Compute the population variance by dividing in step 4, uppercase N, that means it's the population. Compute the variance for the sample, divide by N minus 1. How many ever in your sample? Minus 1. Finally, we're going to take the square root of that variance to get your standard deviation. So here we have another example of text messages sent via cell phone by 50 high school students. We're going to approximate the standard deviation. First thing we do once again is we find the midpoint of our classes. Here we have them. Then we're going to take the midpoint minus the mean. Notice again, we have some negative, we have some positive. Okay, that mean was given to us earlier. So we need to square those. We need to square those so that we can add them together. After we square them, then we add them together. Get quite a large number here. And now we're going to divide that number by N minus 1 for the sample. And we get 5,975. And this would actually be 5,102 10,000ths if we got rid of the 0 on the end here. So we like to say 0.5102. If we take the square root of this, then we will get our standard deviation. And our standard deviation is our approximate spread away from the mean of all the data in the set. So the standard deviation is the approximate distance from the mean of all the data in the set. All right, now you can use the mean and the standard deviation of a frequency distribution if you enter the midpoints and the corresponding frequencies in L2. You're still going to select one variable statistics followed by L1, comma, L2. One variable stats, L1, comma, L2. The output in the last example is presented below when we took a look at it. The value represents the approximate standard deviation. So we have S of x, which is our sample standard deviation, 77.30142433. And we have our population standard deviation of 76.52450588. Okay, using the empirical rule to summarize data that are unimodal and approximately symmetric. So anytime we have a data set that we have that is, again, approximately symmetric, we can put this nice normal curve around it. And they're referred as bell-shaped or normal. We can use the empirical rule. We will go one standard deviation away from the mean. Now remember, since it is a normal curve, the mean and the median are both in the center. So if I go one standard deviation away from the mean on each side, I can figure out that this is 68% of my data. If I travel two standard deviations away from the mean, I can cover 95% of my data. And if I travel 3 standard deviations away from the mean, I can maybe gather all or almost all of the data would be within 3 standard deviations. So we usually call this 99.7. So 68, 95, and 99.7. It's not written on here, but that's normally what we call it. Just means almost all of it. So here we have the U.S. Census Bureau projection for the percentage of population 65 and over for each state and the District of Columbia. We're going to use the empirical rule to describe the data. First, we take a histogram and we put everything in our histogram as we did before. We notice that it is approximately normal. And we might use the TI-84 to find our population mean and our standard deviation over here. So we have our population mean and our standard deviation. Now, if I take my population mean minus my standard deviation and my population mean plus my standard deviation, meaning I'm actually going one standard deviation away from the mean on each end. And I'm going to show you a quick picture of what I mean there. So this would be if I add my standard deviation and if I would subtract my standard deviation, I'd have 68% here. So let's see if this helps. So here I have my normal curve. Here's my mean. If I subtract my standard deviation, I'm moving over here. If I add my standard deviation, I'm moving over here. So all of this area under the curve would be considered 68% of my data. If I do it twice, then I'm going to have 95% of the data. And if I do it 3 times, I'm going to have almost all or possibly all of the data. So here we have, again, showing you 1 standard deviation away is 68%. 2 standard deviations away will be 95%. And 3 standard deviations away, 99.7, or as we say, almost all of the data. All right, now Chebyshev's inequality to describe the data set is used whenever we might not have a bell-shaped curve. So when it's bell-shaped, we can use the empirical rule to approximate it. So if we do not have a bell shape, then we can use Chebyshev's inequality to hold for any data set. So in any data set, the proportion of the data that's within k standard deviations is at least 1, or this should be actually k minus 1 over k squared. Okay? Specifically, by setting k equal to 2 or 3, we can obtain the following set of results. So we have k squared minus 1 on the top. This is k squared minus 1. This is an error right here. Let's see on your what page you can find that. Okay, I'm going to change this so we have this being, it should look like this. I'm sorry I didn't change it beforehand. I didn't catch it until now. So let's take a look at what it should actually look like. We're going to have 1 minus 1 over k squared. Okay, so this is what it is. 1 minus 1 over k squared, okay? 1 minus 1 over k squared. Now, if we take a look specifically by setting k equals 2 or k equals 3, then we're going to find out that we have, and I'll put this up here a little bit higher, that we have 3/4 or 75% is away, 2 standard deviations away from the mean. That's your 2. Okay, 2 standard deviations away from the mean. Or you have 8 over 9, which is 89% of the data within 3 standard deviations away from the mean. So it was found that this is more accurate whenever you do not have a normal curve. So when it's it's, they say it's an inequality, not very equal to both sides, not symmetric to both sides, then you're going to use this, which will just simply give you 75% and 89%, okay? So once I find that, here I have the part of the public health safety systolic blood pressure measured for a large group of people. The mean was 120 and the standard deviation was 10. What information does Chebyshev's inequality provide about this data? Simply, we're going to take the mean minus 2 standard deviations to get 100, the mean plus 2 standard deviations to get 140, the mean minus 3 standard deviations to get 90, and the mean plus 3 standard deviations to get 150. Now we can conclude that at least 3/4 are between the 2 standard deviations, and we can conclude that 8/9 is between 3 standard deviations. Okay, so 3/4, 2 standard deviations, 8/9, 3 standard deviations. So you don't have to worry about figuring out the 3/4 and the 8/9 each time. They have given that to you. You just have to go ahead and do as you did before, taking the mean minus 2 standard deviations, the mean plus 2 standard deviations, and then the mean minus 3 standard deviations, and the mean plus 3 standard deviations, and then concluding that in this case, instead of before where we had 2 standard deviations being 95%, it is now 75%, and 3 standard deviations is now 89% versus what we had before, which we said almost all, or 99.7. All right, we're going to compute the coefficient of variation next. CV for short. Tell how large the standard deviation is relative to the mean. It can be used to compare spreads of data whose values have different units. The coefficient of variation is found by dividing the standard deviation by the mean. So you're taking the standard deviation, you're dividing it by the mean, and that's how you get your coefficient of variation. So here we have the National Weather Service records show that over a 30-year period, the annual participation in Atlanta, Georgia had the mean of 49.8 inches with a standard deviation of 7.6 inches. The annual temperature had a mean of 62 2/10 degrees Fahrenheit with a standard deviation of 1 3/10 degrees. Compute the coefficient of variation for precipitation for temperature, which has the greater spread relative to its mean. So we take each one and we divide it by its mean. Here we will get precipitation, 1500s. Here we will get 200s for our temperature. So our CV for precipitation is larger than the CV for temperature. So therefore, precipitation has a greater spread relative to its mean. All right. Whew, that was a lot of information. So good thing it's on a video. You can go back and refer to it. How to compute the range of a data set. The notation for population variance, population standard deviation, sample variance, sample standard deviation. How to compute the variance in the standard deviation in populations and samples. How to use the TI-84 plus to compute the variance and standard deviation for populations and samples. How to approximate the standard deviation for group data. How to use the empirical rule for a bell-shaped or normal curve set. How to use Chebyshev's inequality to describe any data set, and how to compute and interpret the coefficient of variation. That was a lot of information for one section. So that was section 3.2, and that will be all for that, and I will see you for 3.3.